All right, today we're cracking open a true classic, the Intel 8086 processor. We're going to get right into its fundamental toolkit and figure out exactly how this little engine finds the data it needs to do, well, everything. So let's get into it.
Think about it. Every single thing your computer does, from adding two numbers to rendering some crazy video, it all comes down to the CPU grabbing some data, doing something with it, and then putting it somewhere else. But how does it find that data in the first place? Well, the methods it uses are called addressing modes. You can kind of think of them like different strategies for finding an ingredient for a recipe. Some are super simple, some are more complex, but each one is perfect for a specific job. So, let's start with the most direct, most straightforward methods. Imagine these like having the ingredient written right there in the recipe step, or maybe it's sitting in a labeled jar right on the counter. Absolutely no searching required.
First up is the simplest of them all, immediate addressing. Here, the data is literally baked right into the command. The instruction MOVAX2500H tells the CPU, hey, take this value, 2500, and that H just means it's a hexadecimal number, and move it directly into the AX register. The data is immediate, it's right there. It's fast, it's simple, but as you can guess, not super flexible.
Next, we've got register addressing. Think of registers like these tiny little labeled jars for your most used ingredients, and they're sitting right on the CPU chip itself. So an instruction like MOVAXBX is just telling the CPU to copy whatever's in the BX jar into the AX jar. This is incredibly fast because it's all happening right on the chip. There's no slow trip out to the main memory.
Now here's a really important rule you got to remember. You can't mix and match sizes. When you're moving data between these registers, they have to be the same size. So you can move from a 16-bit register to another 16-bit one, or an 8-bit to an 8-bit, no problem. But you can't try to pour a big 16-bit value into a smaller 8-bit container. It just won't fit.
Okay, so this brings us to direct addressing. Now, the instruction gives the CPU an exact memory address, kind of like a specific shelf number in some massive warehouse. So when you see MOVBL, 2000H, it's basically saying, go to memory location 2000 hex, grab the byte of data you find sitting there, and stick it in the 8-bit BL register. The address is given directly in the instruction.
By default, the 8086 just assumes the shelf number is in a specific section of the warehouse, called the data segment, or DS for short. But memory is carved up into different segments to keep things organized. So what happens if our data isn't there? What if it's in the code segment, or maybe the extra segment? How do we tell the CPU to look somewhere else?
Well, that's where something called a segment override prefix comes in. It's a special little command you stick right in front of the address. For instance, MOVAXES:4321H tells the CPU, hey, listen up. For this one instruction, just ignore the default data segment and go look in the extra segment at address 4321H. This gives you the flexibility to snatch data from literally anywhere in memory, not just the usual spot.
All right, now we get to the really interesting stuff. We're moving away from these explicit, spelled-out addresses and into something that's more like a treasure map. The CPU actually has to do a little calculation, combine a few clues, to figure out where the data really is. This is where the 8086 gets really powerful.
So here we have two modes that are pretty similar, but they have distinct jobs. On one hand, you've got base addressing. It uses a base register, either BX or BP, as a starting point, and then adds an offset. This is perfect for grabbing different fields inside a structured block of data. On the other hand, you have index addressing. It's similar, but it uses an index register, SI or DI, which is absolutely ideal for stepping through an array to get to one specific element.
And, just like before, these modes have their own default behaviors. If you're using the BX, SI, or DI registers to figure out an address, the CPU is going to look in the data segment by default. But, and this is a critical detail for programmers, if you use the base pointer or BP, the CPU automatically looks in the stack segment. This helps keep your regular data separate from your temporary stack data. Now, for all of these, we're adding an offset, sometimes called a displacement, and its size really matters.
See, if we use a smaller, more efficient 8-bit number for that offset, it saves space in our program code, which is great, but it limits our reach. The maximum positive value you can add is just 127. So it's perfect for accessing data that's really close to your starting point.
But what if you need to reach something way over there in memory? Well, that's when you pull out the bigger 16-bit displacement.
Sure, it takes up a little more space in your code, but it massively expands your range, letting you specify a positive offset all the way up to 32,767. It's that classic trade-off again. Do you want a smaller, faster instruction, or the flexibility to access data that's further away?
Okay, for our grand finale, we're going to look at the most flexible addressing modes of them all. I'm talking modes that don't just use one or two clues. They combine multiple pieces of information to calculate the final address with some serious precision.
Based indexed addressing is, well, exactly what it sounds like. It combines a value from a base register, like BX, with a value from an index register, like SI. The CPU just adds them together to get the final address. This combination is super powerful for things like navigating a two-dimensional array, where you kind of need both a base row and a column index.
But why stop there? For the absolute ultimate imprecision, we can add a third piece to the puzzle, a displacement. This mode combines a base, an index, and a fixed offset. So an instruction like MOVAL bracket BX plus SI plus 15 is telling the CPU to do a three-part calculation just to find the exact memory address before it can even go get the data. This is maximum flexibility, right here.
So we've gone through a ton of specific techniques. But if we step back for a second, the 8086 really organizes all of these into two main high-level categories.
The first category is called Data Addressing Modes. And guess what? Everything we've discussed so far, from that super simple immediate mode all the way to the complex based index with displacement, it all falls into this group. Their one and only job is to tell the CPU where to find the data it needs to work on.
The second category is completely different. Addressing modes. These have nothing to do with finding data. Instead, they're used by instructions that change the flow of a program, like a jump or a call instruction. Their whole purpose is to tell the program where to go next, allowing it to branch off to a completely different part of the code.
So there you have it, the 8086's toolkit for finding data. We've seen how simple modes like register addressing are all about raw speed, while the really complex ones like based index with displacement give you ultimate flexibility. And that really highlights a fundamental trade-off that you see in all processor design, giving programmers the right tool with the right balance of speed and power for every single job imaginable. It's something to think about the next time you see your computer's CPU chugging away. Thanks for diving into this with me.